Continue with the next in the series of What is a Matrix, presented by My Simple Math. Here I'll present the physical interpretation of matrices and ways to solve them. Previous videos I expressed matrices as arrays of observations. Since matrices have physical significance, therefore we can express the variables in terms of a quantity. In addition to the arrays of observations, these observations are then some physical quantities. They yield results of the unit measures by taking simple algebraic operations. We can express the variables in terms of a quantity. We can assume anything, say quantities of water, to explain the concept. Here I'll use water as an example to show the physical concept of the matrices, and by an example method of getting the value of the unit measures of the water quantities used in the experiment. One of these methods is Gauss elimination. In order to understand the physical concept of a matrix or the physical significance of a matrix, let's try to take a very simple example. A simple jar of water containing, say, any number. Let's call it 56 ml of water, or just AB ml of water. Now 56 can be written as a product of two matrices, 5, 6 on the rows and 10 and 1 on the columns. Multiply these two matrices together and you would get 56. You could take any other example by increasing the number of elements in this row and the number of elements in this column, say 1, 2, 3, 5 ml of water. Here the coefficients are A and B and the unit measures are small a and small b. Therefore, you can see that all the numbers in a matrix have a physical significance. This goes to show that matrices are actually tractable with physical context, and what better way than to use a simple glass of water. Matrices are composed of numbers, and numbers have a physical context. In this physical context, the matrices are composed of unit measures, x and y, which are to be determined, where 5 and 6, as we have seen before, are the coefficients, and 56 is the total quantity. Let's see how we can use this knowledge, this simple equation right here, to take a simple example of a glass of water. This is easy, it's affordable, and it can be repeated anywhere to give students a better perspective of matrices. The experiment with 3 glasses of water, and each glass has a different quantity of water. Each glass is completely measured by a combination of 3 measures shown below. Let me describe this experiment thoroughly. Here Ki is a different quantity of water in each of the 3 runs, 1, 2 and 3. I goes from 1, 2 to 3. The quantity is measured in terms of the number of unit measures, x, y and z. These unit measures are different from each other, and they are also unknowns. Here you can see that these jars might have some numbers on them, but I put a blue line right here to show that this is the total amount of water that is to be added each unit measure to the glass to make up this quantity of water. And AI, BI and CI are the coefficients. These are the number of unit measures that have to be added each time to make up this total quantity. What is the value of each measure, and how do we determine it? We know that the unit measures defined by these blue lines are unknowns. So we set up the linear equation problem. This linear equation problem right here, it finds applications in a vast variety of applications. Let's solve the problem using matrix and matrix methods. Let's set up the experiment, and after that we collect the data. So we collect the data as unit measures going towards the right, and observations, the number of observations going down. The unit measures are x, y and z. These are unknowns. AI's are the number of coefficients at the number of times that each glass K was filled up with number of unit measures of X, number of unit measures of Y, and number of unit measures of Z. So let's see. The problem was that the data that we collected is split up into two matrices right now here. The matrix of the coefficient, the matrix of the unknowns, and the matrix of the total quantities of water, K1, K2, K3. How does one determine the variables X, Y, and Z? There are various methods to solve this problem, but I'll take the first one. This is the Gauss elimination method. Let's start off with the method of Gauss elimination 1. First, we get the original matrix, and the original matrix we divide the rows by the corresponding coefficients in the first column, that is B1 divided by A1, C1 divided by A1, and K1 divided by A1. Similarly, B2 by A2, C2 by A2. A normalize means just dividing. So for the next step, we subtract row 1 from each of these rows 2 and rows 3. Here I've done the reverse. I've subtracted rows 2 and 3 from row 1, but that should be fine. Either way, it's fine. So B1 by A1 is row 1. B1 by A1 minus B2 by A2 becomes row 2 with a 0 in the first column, 0 in the third column, row 3, and B1 by A1 minus B3 by A3 in row 3, column 2. Similarly, for C1 by A1 minus C2 by A2 in row 2, column 3, C1 by A1 minus C3 by A3 in row 3, column 3, and similarly for the matrix which is K. Now realize and remember that these numbers have a physical meaning here. So we are actually normalizing K1 by A1, means we are dividing the amount of water in the first glass by the coefficient of the biggest unit measure. Similarly here, we continue with the Gauss elimination here, and we say divide row 2 by the coefficient of row 2, column 2. So here it becomes 1, and here it becomes C1 by A1 minus C2 by A2, B1 by A1 minus B2 by A2. And also for column 3, we divide by the corresponding by the corresponding number here, which is column 2, row 3, C1 by A1 minus C3 by A3, B1 by A1 minus B3 by A3. When you divide this number right here, this becomes the denominator for the entire set all the way for the second row for both these matrices. And the number here turns out to be 1 because they are divided. Bear with me in this rigor. I'm doing this algebra here for a purpose, and we'll see that in later presentations. Last step for a 3 by 3 matrix. What we do is we take the row 2 and subtract the numbers from row 2. So we get C1 by A1 minus C3 by A3 minus this number right here, C1 by A1 minus C2 by A2 divided by B1 by A1 minus B2 by A2. This is this is final step of the Gauss elimination process. We get a row reduced echelon matrix, which means that all the elements on the left hand side of the original matrix are turned to 0, and except the diagonal numbers. The diagonal numbers are right here. This number right here is being multiplied by Z, and here is the matrix of K has converted itself into this through these linear algebraic manipulations. This is called the row reduced echelon matrix. And now when we divide this number right here by this number, then you get the value of Z. Z is K1 by A1 minus K3 divided by A3, B1 by A1 minus B3 divided by A3, minus K1 by A1 minus K2 by A2, and so on and so forth. We can start the operations for X and Y. Repeat the operations with the second column as base. You get X. So we get second column as base means k1 divided by b1 minus k2 divided by b2 divided by c1 divided by b1 minus c2 divided by b2 minus k1 divided by b1 minus k3 divided by b3, c1 divided by b1 minus c3 divided by b3, and all of this is divided by the coefficients of the original unit measures divided by each other with these expressions: a1 divided by b1 minus a2 divided by b2 divided by c1 divided by b1 minus c2 divided by b2, and so on and so forth. Similarly, you can repeat the operations with the third column as base, normalized by the third column to start with, and that measure, that linear transformation will give you the values of y like this. Since we are dealing with experiments to explain math concepts, let's put in some numbers in the equations above and check the results. The equations that we had were a1, a2, a3, b1, b2, b3, c1, c2, c3 multiplied by x, y, and z to give k1, k2, k3. I took the numbers as a1 is equal to 3, a2 as 8, a3 as 2, b1 as 6, b2 as 4, b3 as 3, c1 as 7, c2 as 2, and c3 as 5. They yield the numbers 367, 842, and 235. Realize that these numbers 367, 842, 235 are the amount of water in each of the three glasses. And 3, 6, and 7 are the coefficients, which are the number of times that we multiply the unit measures x, y, and z. Now, some of you will be pretty bright and say, well, 3 into 100 plus 6 into 10 and 7 into 1 is 367. So you already took the numbers x, y, and z. I take the liberty to take these numbers x, y, and z as 100, 10, and 1 because it makes it easy, and I am spared with some little effort. But regardless of what numbers you want to put in your experiment, these will always, the solution will be true for almost all the problems. So going forward, what we did was we have to determine whether x, y, and z is really determined by these equations from Gauss elimination or not. So what we did was we substitute the values of k1 as 367, b1 as 6, k2 as 842, b2 as 4, k1 again as 367, b1 as 6, k3 as 235, b3 as 3. Similarly, c1 as 7, b1 as 6, c2 as 2, b2 as 4, c1 as 7, b1 as 6, c3 as 5, b3 as 3. And similarly, for the denominator right here, we substitute the values of a1, b1, and c1 from this matrix. And once you solve all this equation, it comes out to 100, which is exactly what we anticipated it to be. Similar to using the number in the expression of x, we can substitute the relevant numbers in the expression for y given right here, both in the numerator as well as in the denominator. These numbers have been substituted for you right here from these matrices, where the k1 values are taken from here and the a1 and b1 values are taken from here, both in the numerator as well as in the denominator, and you end up getting a value of y as 10, which is exactly as anticipated. I'm showing these values only for x and y because this is frankly, this is too simple. You can take any values of x and y and z here, and it will be correct. Except there's only one thing that I didn't show. What if any of these numbers is negative? If any of these numbers is negative, because our algebra is correct right here, as you have seen in our previous slides, the numbers will work out to be the correct solutions for x, y, and z. What if any of these values were to be 0? Well, for that, I have to simplify these equations right here, because if any of these is 0, say for example C3 is 0, then the entire equation will not be possible to solve it. So for that, I'll come up with another video, and for now, let's move to the summary slide. Summary, I have clarified the matrices and numbers within the matrices as having a physical relevance or a physical context. So our students or young folks who don't understand matrices that well, they can take matrices and not be afraid of them, thinking that these are just bunches of numbers that don't make sense to them. No, they do have a physical sense. And I showed you an experiment to validate the physical relevance of matrices. There are limitations. For example, you can't have a zero in any of those solutions that I just gave you, but still you have a physical relevance of the matrices shown here. And I also introduced the solution of those unknown unit measures in this experiment through the method of Gauss elimination. So in summary, this should put a lot of doubts on matrices to ease and kind of generate more interest in the applications of matrices. Thank you.